Welcome to this explainer. Today, I'm absolutely thrilled to guide you through a radical new paradigm in theoretical physics. We're going to completely redefine the very nature of mass. We'll be exploring a fascinating paper by Sriman Barua on the absolute medium model and the nonlinear elasticity principle, or NLEP. As a researcher, I spend a lot of time looking at different models, and I've got to say, the way this framework reimagines what matter actually is, well, it's a total game changer.
So let's start with a really simple yet profoundly deep question that has puzzled researchers for decades. What actually is mass? Is it just an intrinsic, unexplainable property, or is there a mechanical reality behind it? Let's dive in and see how this new absolute medium model answers that exact question by treating the universe as a continuous, fluid, elastic substrate. We're taking a massive journey today. Our roadmap covers 6 key stops. First, the illusion of mass. Then, the anatomy of a particle, why matter feels solid, scaling up to planets, the extreme matter threshold, and finally, the 8 rules of reality.
Section 1. The illusion of mass, redefining reality. Let's completely challenge what we thought we knew about how matter actually gets its mass.
It's really fascinating to contrast standard field theories with this new fluid elastic view. In standard models, like the Higgs mechanism, mass is essentially an arbitrary label assigned via coupling to a hypothetical field. It's just a parameter plugged into an equation. But in the absolute medium framework, mass isn't just an arbitrary label at all. It's a literal physical consequence of space itself being stretched and spun. Mass emerges directly from the nonlinear elastic strain energy density of the medium.
Think of particle creation like folding a flat sheet of origami paper into a dense, tight knot. The mass you end up measuring is quite literally the geometric receipt for how much of that paper you used. In physics terms, this folded volume is called the absolute baseline equivalence. To calculate this for a proton, for instance, the medium has to forcefully gather exactly 1.50 times 10 to the negative 69 cubic meters of baseline space to hit a strict saturation limit. The mechanical work required to buckle that exact volume relates directly to the total structural energy, which gives us its definitive mass.
And the math behind this is just brilliant. Naturally, nonlinear elastic strain energy wants to diverge to infinity at the causal limit. To stop that from happening, a cutoff parameter, represented by the Greek letter delta, is strictly applied. By integrating this now finite strain energy over the volume, we can definitively prove that under a uniform core approximation, a particle's mass is perfectly proportional to its folded volume. It completely locks in that mass-volume proportionality.
Section 2. Anatomy of a particle. Inside the topological knot. So if we zoom way in, what does one of these folded topological knots actually look like? Let's break down the core skin model.
Picture a fundamental particle, kind of like a hurricane. The frozen core is the uniform, calm eye of the storm, while the active skin is the violently spinning outer wall. What's absolutely mind-blowing here is that at the strict topological scale, every single piece of fundamental matter has the exact same core density. It's 1.11 times 10 to the 42 kilograms per cubic meter. The active skin then fiercely projects outward, deflecting other incoming storms. This happens via the volumetric coupling principle, which beautifully translates internal strain into the macroscopic mass properties we actually observe.
And here's where that cutoff parameter delta does its heavy lifting. Notice how the core boundary integral strictly halts at a finite geometric boundary. In traditional classical point-particle models, integrating all the way down to a radius of 0 gives you a catastrophic mathematical divergence known as the Coulomb singularity. But here, the cutoff parameter ensures those broken singular point particles are physically replaced by finite stable knots. This produces a steep r⁻⁻⁴ short-range potential, completely avoiding the singularity.
Section 3. Why matter feels solid, the mechanical Pauli exclusion. We always hear that atoms are almost entirely empty space. So how does this fluid elastic model explain why everyday objects feel solid?
Why can't you walk through walls? It's the ultimate childhood question, right? Well, the absolute medium provides a completely deterministic structural mechanism for why matter stubbornly resists collapse. It throws out abstract quantum rules and replaces them with tangible fluid mechanics.
To picture this, imagine the space between particles is like oobleck, that non-Newtonian fluid made of cornstarch and water. If you punch it, or if 2 particles squeeze the medium between them, that local space undergoes what's called NLEP shock stiffening. It instantly petrifies, forming a quasi-rigid tension bridge.
Penetrating that ridge requires a diverging amount of thermodynamic work, which mechanically enforces the Pauli exclusion principle and gives us the perceived solidity of matter. You can't walk through walls because the space between the atoms turns to concrete when you push on it.
Section 4. Scaling up to planets, the dual volume metric. Now let's transition from topological knots to macroscopic matter. What happens when we construct an aggregate as massive as the Earth?
Take a look at this massive number. This represents the Earth's apparent volumetric exclusion. Think of this as the fluffy, classical, spatial boundary that dictates standard everyday interactions. It encompasses all the internal, unstrained space of the atomic lattice.
But if we do the math to calculate the absolute baseline equivalence, the actual, pristine geometric volume permanently folded to create Earth's entire baryonic mass, we get this incredibly tiny structural footprint. This vividly proves that macroscopic density is basically just a fluid dynamic illusion compared to the uniform hyperdense core of the particles themselves.
Let that sink in for a second. The solid matter of our entire planet, mountains, oceans, cities, everything, is essentially an illusion created by those active skins. The actual folded volume of space constructing Earth is smaller than a single grain of sand. Literally everything else is just the relaxed, unperturbed medium trapped between those highly compressed knots.
Section 5. The extreme matter threshold, forces and collapse. So, what happens when we push these fluid elastic mechanics to their absolute breaking point under extreme astrophysical conditions?
This is where the model beautifully unites the fundamental forces. In this framework, the strong force and gravity are just the exact same fluid elastic medium expressing itself at different scales. The strong force is a direct consequence of localized saturation pressure, that R to the -4 NLEP shock stiffening at the microscale. Contrast that with gravity, which is just the smooth macroscopic advective flow routing the ambient field, giving us that classic inverse square behavior we all know.
To understand the structural limit of something as extreme as a neutron star, we have to look at topological defects through a three-tier volumetric spectrum. First, the absolute baseline equivalence, the foundational folded core. Second, the apparent volumetric exclusion, the diffuse footprint. And third, the critical degenerate volume, which is the absolute minimal active skin required to keep the knot safely folded under extreme crushing pressure.
This critical degenerate volume perfectly predicts the threshold for black hole formation. A neutron star has all its internal space squeezed out until its nucleons are compressed right to that critical limit. If macroscopic gravity pushes even a tiny bit further, the localized exclusion zones completely fail, the topological cores seamlessly merge, and a black hole forms. And the best part? The mechanics unify to explain this phase transition entirely with the mathematical breakdowns or infinities that plague standard theories.
Section 6. 8 Rules of Reality, Axioms of Persistence. To ensure the universe doesn't literally tear itself apart during these topological phase transitions, the absolute medium relies on 8 foundational axioms.
If we compare this to current field theory frameworks, these 8 axioms are essentially the mathematical padlocks of reality. Their physical significance is that they strictly enforce stability and prevent mathematical singularities. By enforcing a hard, irreversible boundary on infinite strain, they guarantee the physical universe simply cannot be pushed past a specific mathematical threshold. So instead of a catastrophic collapse into a point of infinite density, the axioms enforce a clean, stable, discrete phase transition.
I really want to highlight one of these rules, the persistence inequality. For a particle to remain stable and persist through time, the localized resolution rate of the medium, basically how fast space can heal itself, must continuously exceed the generation rate of structural strain. It's this continuous, dynamic balancing act that maintains stability. It proves that particles aren't static little rocks. They are highly dynamic, persistent vortices of space.
Removing mathematical singularities fundamentally changes our understanding of particle physics. It strips away arbitrary coupling mechanisms and replaces them with tangible, fluid elastic geometry. And as we leave those old singular models behind, it leaves us with an incredibly profound question. If mass is simply the geometric receipt for folded space, strictly governed by these rules, what truly lies beyond the critical limit of reality, when space itself completely runs out of room to fold? Thank you so much for joining me on this explainer. I hope this shift in perspective was as eye-opening for you as it was for me.